In this video, we shall see the input and output impedances of common drain and common gate amplifiers. So this is the common drain amplifier. So the input is applied to the gate. R1 and R2 are the biasing resistor. CC is the coupling capacitor. The output is taken at the source point. The RS is the source resistors. The AC equivalent circuit of the CD amplifier with lambda 0 is given by this. Now we have R1, R2 coming in parallel here, and this is the representation of the MOSFET GM into VGS. RS is the load resistor over here, so which is RS. So V naught is taken here. Now let us try to find how do we find the input impedance. We know that to find the input impedance at the input we are connecting a dummy source Vx. So we need to measure the ratio of Vx by Ix, which happens to be the input impedance. Writing the KVL at the input loop. So we know that Vx is given by Ix multiplied by R1 parallel R2. So naturally Vx by Ix happens to be R1 parallel R2, which happens to be the input impedance. So let us see how do we find the output impedance of the CD amplifier. We know that to find the output impedance, we are shorting the input voltage. I can say this is input voltage shorted here, and input voltage is applied. A dummy source of Vx is applied at the load here. And this is the Vx. The ratio of Vx by Ax happens to be the R out. So since this is short circuited, so the VGS, the voltage across VGS happens to be minus of the drop at this point, which is nothing but minus into Vx, where minus into Vx happens to be this voltage. The Vx is applied here. The same thing is coming with a negative polarity here. So VGS is minus Vx. Writing the KCL at node 1 here. This is node 1. The current entering the node is Ix. So this is Ix. And one more current that is entering the node 1 is GM into VGS. The current that is leaving is this I0. The KVL says that the outgoing current is equal to the sum of the incoming currents. So the outgoing current in node 1 is I0. The incoming currents are Ix and the GM into VGS. So replacing this VGS by minus Vx and I0, the current that is through RS by Vx by RS. So by rearranging the equation, so we get Vx by Ix is nothing but 1 over Rs plus Gm. So this exactly means that this 1 divided by 1 over Rs plus Gm is actually the parallel combination of Rs and 1 over Gm. So R out, the output impedance of the CD amplifier looking into the source at Rs happens to be Rs in parallel with 1 over Gm. So this is what we are seeing here. This is a CD amplifier with lambda 0. If you see from the input side, which is input here, now it is R1 parallel with R2. Looking at the output, so now we can see this is looking up from the source point, it is 1 over Gm because lambda is 0. Looking down here is Rs. Looking from the output point, it is 1 over Gm in parallel with Rs. So this is Rs, that is 1 over Gm. So overall R out is Rs in parallel with 1 over Gm. Let us consider the same CD amplifier with the lambda non-zero. Now you can see we have connected R0 between drain and the source, and a dummy source Vx is applied the input voltage, and we have this Rs, which is the resistor at the load point. Now let us try to find out what is the Vx by Ix. So Vx by Ix, from this observation, by writing the KVL at the input loop, Vx happens to be Ix into R1 parallel R2. So naturally the input impedance of this CD amplifier with lambda non-zero happens to be R1 parallel R2. So let us find what is the output impedance. So we know that for output impedance we are shorting the input source here. So this is short circuited. We are applying a Vx source across the Rs where we are measuring the output voltage. Now writing the KCL at node 1. So this is the KCL at node 1. So we know that the incoming currents are this I2, that is current through R0. This is I2, we named it as, and there is one more current which is going here. This is Ix, and there is another current, third current, which is GM into VGS, and these are the incoming currents to at node 1. The outgoing current we assumed it as I1. So this is I1. So we know that this VGS is actually minus of Vx, because this is Vx plus here, negative is at this point, which is actually going reverse direction at the VGS. So this is VGS is minus Vx. Similarly, I2, the current flowing through this R0 is nothing but the potential here is 0, that is ground here. The potential at this point is Vx. It is 0 minus Vx by R0. So this is the current I2. So naturally current I1, the current that is going through Rs is nothing but Vx by Rs. So substituting these values onto the equation what we have. So I1 is nothing but Vx by Rs, and I2 is nothing but this is minus Vx by R0, and of course this is Ix retained as it is. Gm into Vgs can be written as Gm into minus Vx, because this Vgs is minus Vx here. So rearranging the expression what we have here. So Vx is given by this expression. So now Vx by Ix is given by 1 over Rs plus 1 over R0 plus Gm, which exactly the parallel combination of Rs parallel with R0 parallel with 1 over Gm. Meaning, if you look from the this is the CD amplifier summary. With lambda 0, if you look at the input, it is R1 parallel R2. With lambda 0, the output impedance is, if you look up here, it is 1 over Gm. If you look down from that output terminal, it is Rs. The overall output impedance is 1 over Gm in parallel with Rs. With lambda non-zero, looking at the input impedance, it is again R1 parallel R2, same as the previous case. Only change happens in this, because we know that with lambda is non-zero, looking towards the source side, it is 1 over Gm in parallel with R0. So looking down here is Rs. So R out, that is looking at this point into the circuit, is 1 over Gm in parallel with R0, that is in parallel with Rs. So that's what the expression what we have. So R out is nothing but Rs in parallel with 1 over Gm in parallel with R0. That's what we saw in the derivation also. Now you can see this is what is R out. Rs in parallel with R0 parallel with 1 over Gm. Now this way we can find the input and output impedance of CD amplifier for both lambda equal to 0 and lambda equal to non-zero values. We shall see now the CD amplifier input impedance. So this is the CD amplifier where the input is applied at the source terminal. R1 and R2 are the biasing resistors which will provide the DC bias, and RD is the load resistor which is connected to the drain. So now you can see this gate is grounded, AC grounded, because at the gate we have only the DC voltage which is due to R1, R2 and VDD. That's why we are not representing it by R1, R2, it is simply grounded here. So this is VGS, and since we consider the case of lambda equal to 0, so it is the MOSFET is represented by at the drain and the source side Gm into VGS, and RD is connected to the output, that is between drain and the ground. So looking at this, the input impedance is nothing but, okay, we are considering this input is replaced by a dummy source Vx. So we want to find what is Vx by Ix. So we know that this current Ix is actually in the direction opposite to that of Gm into Vgs. So Ix is minus Gm into Vgs. But this Vgs between gate and the source is exactly minus of Vx. So Vgs is equal to minus Vx. So from it we can write Ix is equal to Gm into Vx. So from this we can write Vx by Ix. The ratio of the voltage by the current is nothing but Rin is nothing but 1 over Gm. Meaning the input impedance of a CG amplifier looking towards the source is 1 over Gm. Let us find what is the output impedance. Now we know that to find the output impedance, this is short circuited, where we are supposed to apply the input voltage, and we are connecting a dummy source at the load over here. So now this is because this is short circuited, so VGS becomes 0. When VGS becomes 0, so this current source becomes an open circuit. Now you can see it is open circuit. So as you can see here, so writing the KVL at this point is Vx is given by Ix into Rd. So naturally Vx by Ix happens to be R out, which is nothing but Rd. The output impedance of a CG amplifier with lambda non-zero is given by just Rd. Let us consider a case where lambda is non-zero. Let us try to find the input impedance. We know that to find the input impedance, we are connecting a dummy source here. We are grounding the gate because gate is providing the DC voltage. We are connecting a R0 between drain and the source. This is R0. So let us write the KVL at node 1 here. This is node 1. So we are considering this current is going towards the node, and this is also going towards the node, and we are assuming this current is also going towards the node. So writing KCL at this point, which is nothing but Ix plus Gm into Vgs plus I1. So all the currents are going into the node and none of the current is leaving. So that's why Ix plus Gm into Vgs plus I1 is equal to 0. So we know that this VGS is actually minus of Vx. So because this is ground, and this polarity is common here. So VGS can be written as minus Vx. And I1, whatever current that is flowing through R0 is nothing but the potential difference at this point and this point divided by R0. So potential at this point is at this point it is Ix into Rd. So that's what we have. The current I1 is Ix into Rd minus of Vx and divided by R0. So this is the current flowing through R0, and we can write the expression for this as Ix minus Gm into Vgs minus Vx by R0 plus Ix Rd. So this is the expression. Of course, this will be equal to 0. By rearranging this expression, so we have the ratio of Vx by Ix. So Vx by Ix happens to be, so this, that is R0 plus Rd by 1 plus Gm R0. So that can be written in this way. Now I am just splitting this R0 by the same ratio plus Rd by the same ratio. Since neglecting 1 compared to Gm into R0, so it can be written as R0 by Gm R0 plus Rd by Gm into R0. So this can be further written as 1 over Gm plus Rd divided by Gm R0. So this is the input impedance of a CG amplifier, meaning looking into the input impedance of the CG amplifier with lambda non-zero, it is not simply 1 over Gm. So this is 1 over Gm when it is lambda 0. When lambda is non-zero, we are having one more term that is coming. It is Rd divided by Gm into R0. So it is only this much if lambda is 0 plus another term if lambda is non-zero. So same can be proved by taking the currents at node 2, which is again the representation of the Rin. Now this is output impedance of CG amplifier with lambda non-zero. This is actually, sorry, this is CG amplifier. By mistake it is written as CD. I can see the input is made 0 and gate is grounded because it is providing only the DC voltage. Since Vin is 0, VGS happens to be 0. So this is open circuited. So we have R0 between drain and the source because we have considered lambda non-zero. By applying a dummy source Vx at the output node, so we have Vx by Ix given by, now you can see this is grounded, so R0 is coming in parallel with Rd. That's what is equivalent circuit. So Rout happens to be Rd parallel R0. So when lambda is non-zero, so Rout was only just Rd. Let us have a summary of this CG amplifier input and output impedance when lambda 0 and lambda non-zero. When lambda is 0, the input impedance from the input happens to be 1 over Gm, and the output impedance is, okay, looking down here it is infinity, looking up here it is Rd. So Rout is Rd parallel with infinity, so that's why it is Rd. So looking up here, since it is the source, looking up it is 1 over Gm. So similarly here, when lambda is non-zero, looking up towards the source is 1 over Gm parallel with R0, so this is Rin. Looking down here is R0 from the drain side, looking up here is Rd, so Rout happens to be Rd parallel with R0. Of course, we'll also have a CG amplifier with some resistance which is allowing the current to flow through this. We'll analyze the input and output impedance of this CG amplifier